Good morning, everyone. This is Shauna, and I'm here this morning to record a brief walkthrough of section 7.2. Let me go ahead and share my screen at this time. 7.2 continues the uh, concepts that we started in 7.1. We're still doing confidence intervals estimations. This is when we don't have sigma, when we don't have the population standard deviation. And so this is going to involve a different distribution than we used in the previous section called the T distribution. Let me show you some slides here. The first thing to be aware of is the characteristics of the T distribution. This is on 2 slides, and it's actually the first question that's on your homework. I'll show you that in a minute, but let me just go over this. So this is a different distribution than the Z's, but it does have a lot of similarities. So it is bell-shaped like the Z distribution. It is symmetrical about the mean, so the mean is in the middle. The mean, the median, and the mode are all equal to 0 and are located at the center, and the curve never touches the y-axis. Now, or that, sorry, the x-axis. So those ways, it's similar, okay? Although with a t, the mean is 0, okay? Unlike the z, where it can be other numbers. But there's it differs in that the variance or the standard deviation, because remember the variance is the standard deviation squared. So in a Z distribution, the standard deviation is equal to 1. We know that from a standard normal, right? But the variance is greater than 1. The T distribution, this is the difference, the biggest difference for us. The T distribution is a family of curves based on the concept of degrees of freedom. And the degrees of freedom is always 1 less than n, 1 less than the sample size, which we're going to come to in a minute. As the sample size increases, the distribution approaches the standard normal. So that's where this assumption where it says n is 30, here it's n is less, because if you're doing a less than 30 situation, think of T, the T distribution, T for tiny. When the sample size is small, it's a different distribution. Once you get around 30, once you get 30 or more, it usually starts looking a lot like the normal distribution. And that's what you can see here when she's shown you different distributions for different ends. You have the blue one, the dark blue one, and the black one. The black one is the Z. The 2 dotted ones are T distributions for different degrees of freedom. And you can see how much flatter the distribution is when DF is equal to 5, which would mean the sample size is 6, for example, than when it's equal to 20. Again, I'm going to come back to the degree of freedom. This is your formula for the confidence interval. Again, notice that the left side and the right side are very similar. This is a confidence interval for the mean. So we have X bar. Instead of Z, we have a T alpha, okay? Instead of sigma, we have S. Those are the differences in the formula, okay? So once again, we have T alpha 2 and instead of sigma, we have S. The terms are the same. T alpha 2 is known as the confidence coefficient. T alpha 2 times S over the square root of N is the marginal error, and S over the square root of N is the standard error. DF is equal to N minus 1. DF is this degree of freedom. That's the difference. We have a different procedure for finding confidence coefficients. Again, very similar. Alpha is 1 minus the confidence level. The area here is from negative infinity to the T alpha 2 line. I have to show you the calculator piece of this because it's a different function than before. The other thing that's critical in this situation is when you distinguish when to use the z distribution versus the t. Let me show you something on the homework before I show you that. So if you look at the homework, okay, what are the properties of the t distribution? I just showed you those properties. I showed you all the properties that made it like the z distribution and all the properties that made it different. So those two slides that have the properties, that's where you're going to go. I'm going to come to this number 2 in a minute. Okay. And then you and I will do a problem together. We're going to do number 4 together. Okay. But the thing is, on the exam or the quiz, Professor Nickdell is not going to tell you which distribution to use. And so, and the answers are going to be fairly close. She's not going to accept it if you use the wrong distribution. This is why you have the flow chart. So when you're reading the problem, you have to answer these 2 questions that are here on the left. The first question is sigma known? Do I know the population standard deviation? If you do, then you're back in 7.1, essentially, okay? Is sigma known? Yes, then you use the z value for any sample size you have, no matter how big or small it is, okay? Is sigma known? Yes. If not, if it's not known, okay, then if you answer no to this question, okay, then you ask yourself, is my sample size greater than or equal to 30? Okay, so if I don't have the population standard deviation, but I have a large sample, okay, then I can still use the z value, okay? I can still use the technique from 7.1. I just use the sample standard deviation, S, in place of the population standard deviation, sigma, due to the central limit theorem. So the fact that n is bigger than 30 allows me to use the sample standard deviation because the distribution will approach normal, okay? That's what this says. Okay, most of our situations are going to give you 2 no's. Do I know sigma? No, I don't. And is n greater than or equal to 30? No. If I get 2 no's, I'm going to use the t distribution. If I get one of those to be yes, then I'm going to use the z either with sigma, like I did in 7.1, or with s, due to the central limit there. But you need to show this work, and I'll show you what that looks like in a minute. But this slide is critical, so keep this slide handy. And while I'm on the slides, question 1, dealt with the characteristics. Those are on slides 2 and 3. Okay, question 1 of the homework. Now, before we can, I'm going to go back to the homework here. Before we can actually form the confidence interval, we have to know how to get my confidence coefficients for t's, okay? And so in order to do that, we have to know two things. We have to know what the sample size is, and we have to know what the level of confidence is, which is why these are given to you. Notice that in here, and this is something for you to know. For example, if you memorized the confidence coefficients for Z as 1.96, do not use them here, okay? These are T distributions. These are different, and they differ for every sample size. So be very careful when you're doing, especially when you're doing the exam or the quiz, that you pay attention to whether you're on the Z or the T distribution, okay? Because sometimes what students do is they substitute those values and they shouldn't, all right? So be careful with that. But let me show you how this works. So 2A says find the values for each. T of alpha 2, if n is equal to 18 for the 99% confidence interval, okay? So this is what this is going to look like. I'm going to bring up the calculator and I'll show you this. So here, I'm going to come back to this data in a moment. Second, quick. We're going to come back to that. All right. So here I have 2A, and I want to find the confidence coefficient for a T distribution with n equal to 18 and your confidence level of, was it 99? Let me see. Let me go back, look at the homework really quick. This was, yeah, 99. So let me come here. Oops. And my annotation disappeared. Give me a second. So I'm going to find the confidence coefficient for a T distribution with n equal to 18 and confidence level equal to 99%. Now, if you remember what we did in the previous section, this is very similar. So you draw your distribution. You don't have to draw it. You can use the mechanics that Professor Nickdell gave you. I like to draw it so you can see where it comes from. But we have a confidence interval here. And we're looking for this T of alpha 2. Remember, again, we have a positive and negative, just like the Z, but we're looking for the positive one. We're looking for the one on the right. So here, this is going to be your confidence level 99 in here. So this is going to be 99% right there. Now, my alpha is 1 minus the confidence level. So what's going to happen is I have alpha is going to equal 1 minus my confidence level, which is 1 minus 0.99. And that is going to equal 0.01. Now remember, that's my area in both tail, okay? So what happens is that each of these areas here, each of these areas in the tail is 0.01 divided by 2, right? Which is 0.005. This is 0.01 divided by 2. This is a picture of what's going on. Do you have to draw it? No, you don't. But I sometimes find that it's helpful for students to understand what's going on. So now, this is what we have here. We're looking at this area from negative infinity to the T alpha 2 line right here. Okay, we're looking at all of this. So not just 99, but this half tail piece as well, okay? Now, on your calculator, instead of, remember when we were doing Z, it was inverse norm. So we're gonna go second, distribution. In chapter 6, we were doing normal CDF and inverse norm. Now we're gonna do inverse T. We're gonna look at this inverse T number 4, okay? Most of your calculators should have this. If for some reason your calculator doesn't have it, Professor McDowell has programming instructions for you. And a handout if you need to program your calculator, or if you are in class, she's going to give you programs, okay? And this could be one of them, but most calculators have this. There are some other programs that she's going to give you that your calculator doesn't have that we need for later chapters. But we're going to go to number 4, inverse T. And the inputs for inverse T are very similar to our inverse norm. So we're going to do 1 minus, and again, here use the big minus, 1 minus alpha 0.01. That's why I had to get alpha. 1 minus alpha divided by 2. Yes, you can simplify that and put in a single number, but if you'd rather put in the expression, you can as well. Now, DF is degree of freedom. Degree of freedom is n minus 1 all the time for T. So here, my degrees of freedom which we abbreviate as DF, are equal to n minus 1, okay? And so here, if n is 18, then the degree of freedom, if DF is equal to n minus 1, and DF here is 18 minus 1, then DF is 17. And that's all you have to do. So this is, we have enter that, and then we come down. I use my arrow keys. I'm gonna come down here. 17 is my degree of freedom. Paste it in. And there's my number. And the T's are usually 3 places. So 2.898 would be my T. So my T here would be T sub alpha over 2, which would be T alpha over 2 would give me this number that you see on the screen. Okay, so this is going to be 2.898. Okay, and that is how I would get my T's for not only my the exercise here, but also for my confidence interval. Note that you're gonna have to do this procedure. You don't have to do the drawing, but you do have to do this inverse T for each confidence interval because it changes based on your sample size. So you'll want to do this procedure. I just drew it so you can see what we're actually doing. Okay. All right. So here, if we go back to the homework, okay, then we have, let me scroll down. That was number 2. And as we can see, 2.898. Okay. So that's 2A. You do the other ones in a similar way. All right. Now I'm going to show you one other one. We're going to actually apply all of this and form an interval. Okay. So it says, I'm doing number 4 right now. A state representative, excuse me, wishes to estimate the mean number of women representatives per state legislature. So the first thing to notice here is we're estimating the mean, okay? Whenever you're estimating a mean, you're going to have 2 choices, a 0 T, per state legislature. A random sample of 17 states is selected, and the number of women representatives is shown. These are my data. These are, when you hear her refer to raw data, okay, raw data is this down here. This is raw data, okay? And when you're dealing with raw data, that means you're using the calculator, okay? Based on the sample, what is the point estimate of the mean? Okay, that's the first question. And then find the 90% confidence interval of the population mean, of the mean population, right? Note that the population mean is actually 31.72. Now, they're telling you that the population mean, they're giving you mu, which we don't know that, but the purpose of this here is to help you compare your result with theirs and see what's going on. Okay, they're making up a larger point about the data. So let's take a look at what they tell us. This is 90 and we have 17. So now I'm going to go to the calculator again. And we're going to do some work. Okay, now we have some notes here. So I'm going to make a couple of notes. We're looking at, we want to form, so this time we want to find a confidence interval. Okay, find a confidence interval for the population mean when n is 17 with 90% confidence given the data, okay? Given the data on the calculator. Now I'm going to show you that in a minute, okay? So here's what we're dealing with, okay? Now to save us some time, I went ahead and put the data in our calculator. So I'm going to show you that. So stat, edit, okay? There's my data. Okay, this is the same data that you saw in the problem. You know how to enter data. So go ahead, pause the video, enter the data into your calculator if you'd like to follow along. Okay, so here's my data. Now what I'm gonna do is the first thing I'm gonna do is figure out which, so step one, I'm gonna come over here. And I'm going to write some stuff out on the whiteboard. Okay, we're gonna do some data in a minute here, but I'm going to do some work with some of the stuff. So step one is we're going to write out what we're given. So step one here, step one is to write out the given. So we're gonna say, now we need a couple of things, okay? So step one, we're gonna write out the given data. And we're gonna say that we have this is okay. So we're gonna say, now the thing is, we don't know a couple of things. We don't know what the mean is, and we don't know what the standard deviation is. We do know we have 17 data, not only because they tell us, but we can count the data, and we're gonna do that. N is 17, and I should have shown you something here. Let me do this like this. So I'm going to say, let me go back to the calculator here. This is my calculator screen here. But I want to go back and show you the okay, I'm going to go ahead and shrink my view. So my calculator screen, if I go to stat and I go to calc and I go to one var stats, okay, I'm gonna calculate it, and I wanna go ahead and I think I have, yeah, I have L2, I want L1. My apologies. So my mean here is 33.3529. Okay. So my mean is 33.3529. I need that. And I also need SX, which is not sigma X, it's SX. SX is 28.6878. 28.6878. So now I'm going to go back to my Zoom here. And I'm going to show you that I have some values. This is, okay, so I'm going to come up here and I'm going to say that SX is equal to 28.6878, and my X bar my sample mean was 33.3529. Okay. So now I'm going to use those data to construct my confidence interval. Notice that because I had raw data, I had to put those in there. So now I'm going to go ahead and show you the other part of this. So I have my board and I say, all right, so remember that X bar, so this is X bar minus T sub alpha over 2 times S over the square root of N. Okay, so this is S over the square root of N is less than mu less than X bar plus T sub alpha 2. S over square root of N. Now we also need the T value. So what I'm going to do here is we have our information for our T. So we're going to, now I should have said, let's answer the questions up here. Here's my data, right? I've got my S, I've got my X bar. This is X bar. Now, my questions are, what are the questions? Well, remember the questions came from the flow chart. So question one was, question one is, is sigma known? And the answer was, no, I don't know sigma, okay? No, this is raw data, I don't have it. Question number 2 is, is n greater than or equal to 30? And I think you can see if n is 17, that's not bigger than or equal to 30. So the answer there is no. So since we now have 2 no's, okay? So since the answer to both questions is no, use a t distribution, okay? Use a t distribution. And that's exactly what we're going to do, okay? So is sigma known? Is n greater than 30? Since the answer to both questions is no, use a t, and hence that's where we are. Now the next step is to find your t, okay? So remember, we're doing 90%. So the next step to this is to find, step 2 is to find the confidence coefficient, it's called, okay? Whether you're doing a z or a t or any kind of interval, those are confidence coefficient. Find the confidence coefficient. So remember here, we know that n is 17. We know that df is equal to n minus 1. So that means 17 minus 1, or 16, is 17 minus 1, which is 16. And we know that the confidence level, I'm going to abbreviate that CL, is 90%. That comes from the problem itself, okay? We're going to find the confidence coefficient. So I'm going to go to my calculator again. And I'm going to go ahead and come back to that. So I'm going to say, here's my calculator. I'm going to share the screen again. So I'm going to say, okay, here's my calculator screen. Share the screen with you. There it is. So we're going to say second distribution, inverse t number 4. Here I have now, it's not in, remember here, I'm going to clear this. I should have shown you this on the other screen, but I can do it here, not a problem. This is going to be, let me quit from there for a minute so I don't confuse you. So here we're looking at we know we're using a t distribution, and we know that df is equal to 16, because remember it's df is 16. Confidence level is 90%. Okay. So alpha is 1 minus the confidence level. That means alpha is 0.10. So alpha is 0.10. And so our t, which I'm just going to write t is equal to, you should write t alpha too. I'm going to do that after I type. T equals, this is going to be inverse t of 1 minus, remember alpha is 0.10, so you get 1 minus 0.10 divided by 2, and 16. You have that, okay? And so let's do that on the calculator. Here's the mouse. So we have second distribution, inverse t, 1 minus 0.10 divided by 2. df is 16. And we paste it. And that gives us 1.7459. 1.7459. So T sub alpha 2 is equal to 1.7459. Okay. She may round this to 3 and call it 1.746. Okay. A lot of times we round T's to 3 places. So follow the rounding directions there. So here we have that. Now we're going to actually form the interval. So this is our data here. Oops, that was very bad. Let me this is I just want to fix that. So this is going to be alpha 2. So now we have this. And so now we form our interval, right? Remember that x bar was 33.3529. So we have 33.3529 plus, or actually minus on this side, minus my t, which is 1.7459 times my s, which was 28.6878, 28.6878 divided by the square root of n. Be careful here not to square root the df, okay? That's a very common mistake. You're square rooting n, which is 17. So here, this is the square root of 17. This is the square root of n. So be careful there. This is 17 here. So I'm going to say that. And this is going to be my left-hand side of my interval. Okay, so we're going to say that this is, there it is. So we're going to say, all right, let's put this in and see what we get. 33.3529 minus 1.7459 times 28.6878 divided by the square root of 17. Okay, second square root 17. So the left side of my interval here is 21.2. Okay, now the only difference on the other side is going to be the plus sign. Okay, so all I'm going to do is I'm going to do my little trick that I showed you if you watched the video for 7.1. I'm going to go, you can use the arrow keys and grab this expression, or you can do what I'm going to do and use second entry. And it's the same thing, except I'm going to go back, and where there's a minus, I'm going to put a plus sign. And that gives me 45.5. So my interval here is going to be, okay, so my other side, this is going to be 33.3529. That's 3525. You know what? I need to fix it because I just realized I have a typo there. I put 3529, it's 352. Yeah, this is, the calculator is correct. I wrote it wrong on the screen. So let me type that again. Let me go back and type this again. So this is gonna be, let me put it over here. So there's more room. This is 33.3529 and not 3525. 3529. And this is going to be minus my 28.6878 divided by the square root of, I'm just going to write it this way, square root of 17. And that's going to equal, this is my left-hand side, this is 21.205. If she takes it to that many. And the other side of this is 33.3529 3529 plus 28.6878 divided by the square root of 17. And that comes out to equal 45.5 005. So depending on how many places she's taken it, that means our interval here is going to be, if I take it back, it's going to be between 21.2052 is less than mu, less than 45.5005. So that's my confidence interval. Now, if you remember, we were comparing this to the real mean. So let me get a new share. This was about 21.2. So when we did our interval, it was between about 21.2, 21.2 less than mu, less than 45.5, roughly, right? So it says, what is the point estimate of the mean? The point estimate, remember, was X bar. And that was X bar was equal to 33.3529. Okay. That was my point estimate. We found the 90% interval, which is over here. Note that the population mean is actually 31.72. Is 31.72 in the interval? Yes, it is. Okay. Compare this value to the point estimate and the confidence interval. Well, 31.72 is in the interval that we got, but it's lower than our X bar. Okay. And it says, compare this value to the point estimate. There's something unusual about the data, talking about these data over here that she gave you, the raw data. Describe it and state how it would affect the interval. Well, if you do, you don't have to do the math to actually show this, but it's fairly obvious that 132 is significantly larger than any of these other numbers. And you might think 5 is significantly lower, but if you actually do the outliers analysis, which might be good practice. I was back in chapter 3, okay? But if you do the outlier analysis, you'll find that 132 is the only outlier in the data. So essentially, what is unusual about the data is this outlier. So let me show you what she wrote down here. Come down here to the answer key, right? Here's our numbers. She rounded everything to 1 decimal place. So instead of 33.35, she used 33.4. S was 28.7, and that accounts for this 1/10 of a discrepancy in my answer versus hers. But if you round our answer to the nearest 10, it was 45.5550, something like that. This will be 45.6. That's how you get the answer. The point estimate is 33.4 and it's close to 32. The interval does contain 32, okay? The data value of 132 is an outlier. The mean may not be the best point estimate in this case. So it's the most unbiased estimator we have, but it may not be the best because what the outlier is doing is it's skewing the distribution, okay? So I just wanted to go over that. That was a good problem to sort of analyze it. The other problems are similar. It looks like her confidence intervals are rounded to the nearest 10th. Just follow whatever the rounding instructions are on the quiz. But just know that if you're slightly off by a 10th or few hundredths, it's probably round off error doing it. So I hope that has helped you with the material from 7.2. I'm going to sign off for this video, and I'll see you soon in my next video, Lord willing. Take care, and bye for now, everyone.